So now let's keep going in section 22.3 on talking about standing sound waves. Now we'll talk about standing sound waves in open pipes. So we will be back on starting at the bottom of page 446 and moving on through page 447. So we're going to have the same approach here as with closed pipes, and with open pipes, once again, we're talking about a pipe that's open on both ends. And so I'm going to recreate the sketches at the top of page 447, and then we'll develop a general equation for wavelength and then also a general equation for the frequency of a standing wave in an open pipe. So here's the first sketch, which is the simplest standing wave you can have with an open pipe. Once again, the open ends act as antinodes where you get the maximum pressure and also the loudness. The way you remember with a standing wave in a string, we could see the standing wave in a string. The way that you'll recognize a standing sound wave would be an amplification of the sound, so you'll hear it rather than see it. So here's the simplest standing wave, and you have, again, an antinode on each end and a node in the center. And how much of a wavelength are we seeing? So you have a quarter of a wavelength here, a quarter of a wavelength there. So the length of the pipe represents half of a wavelength. And if we solve that expression for wavelength, that equals 2L. For the next possible standing wave in an open pipe, it would look like this. So you're seeing a quarter of a wavelength, half of a wavelength, quarter of a wavelength. So that all adds up to a full wavelength. So we could say that the length of the pipe equals the wavelength, and also the wavelength equals the length of the pipe. And we'll just do one more so we can see the trend developing here. The next possible standing wave in an open pipe would look like this. So you have a quarter of a wavelength, a half of a wavelength, half of a wavelength, and another quarter of a wavelength. So if you add that up, you have 3/4 and 3/4. So you have a 1.5 wavelengths. Now we'll express that as a fraction. So the length of the pipe is equal to 3/2 of a wavelength. So we'll solve this for wavelength. Wavelength then would be equal to 2L over 3. So really what that's telling you, 2/3 of the length of the pipe is sufficient to see a whole wavelength. So this whole wavelength in here just represents 2/3 of the length of the pipe. So we have this expression, and we have this one, and we have this one. Okay, so I'll make a couple of minor mathematical adjustments to these expressions. So I'm going to place a 1 in the denominator for the simplest standing wave without changing its mathematical value. And then I'll take a little more license here. For the second standing wave, I'm going to place a 2 in the numerator and also a 2 in the denominator without changing the value of that expression. So you can see that we can develop a general expression. We have 2L in the numerator and the denominator is 1, 2, 3. If we continued and did the next, sketch the next standing wave, then you'd find a 4. So So the general expression for an open pipe standing wave for the wavelength would be 2L over N. And in this case, all of the N's appear and are available. So we're not skipping any N values like we did with the closed pipe. So we can go ahead and finish and complete our table of N values. So for an open pipe, N equals 1 is the fundamental frequency. And then we have first overtone, so you can see why it's important to have that table available. So as an example, the fifth harmonic would have the same frequency as the second overtone because they both have the same N value. And the seventh harmonic would have the same frequency as the third overtone for a closed pipe. Okay, so now let's keep going here. We need to do the next couple of steps to develop our frequency equation for an open pipe. So far we have the wavelength. All right, so once again, this is a periodic wave, so speed is equal to frequency times wavelength. Frequency is equal to speed divided by wavelength. And once again, we're talking about the speed of sound in air, so we'll calculate that the same way as we were doing for a closed pipe. And then we'll take this expression, substitute into the denominator. So you have frequency is equal to speed divided by 2L over N. And if we multiply the numerator by the inverse of the denominator, you have frequency is equal to NV over 2L. For an open pipe. So let's demonstrate this using the example at the bottom of page 447, example 22.5. So in this example, you're actually being asked to calculate the length of the pipe, and you're given everything else that you need. You're given that the second overtone standing wave for this open pipe has a frequency of 1800 hertz, and instead of having to calculate the speed of sound in air, it's just given to you as 340 meters per second. And the question is, what is the length of the pipe? You're told that the pipe is a brass pipe, which is interesting but doesn't enter into the equation. Okay, so what you're given is Second overtone frequency is 1800 hertz. The speed of sound in air, 340 meters per second. And then you're asked for the length of the pipe. So we're going to solve this equation for the length of the pipe. So L is equal to NV over 2F. Just cross multiplying the L and the F. Second overtone, open pipe from your table, N equals 3. And as we've discussed before, I would not enter the frequency as 1800 hertz. I would enter it as 1800 cycles per second. That way you can do an analysis of the units and make sure they turn out okay. Because if the units don't turn out, then you have not manipulated the equation properly, or you've done something else not quite right. So cycles cancel out, seconds cancel out. You're left with meters, which is appropriate for the length of a pipe. And this results in 0.283 of a meter. And in the textbook, they also converted it to centimeters. Okay, so that is the frequency of an open pipe standing wave. And here are two end of chapter practice problems to add to the ones we already assigned, 9, 10, and 13 for closed pipe. The two open pipe problems, end of chapter 22.8 and 22.11, so you can work on those. And there is one more worksheet I'd like you to take a look at. So if you could turn in the workbook, let's see where that is. All right, back in the workbook, pages 141 and 142. So what you'll notice in this worksheet on page 141, you're asked to take a look at some standing wave sketches. Some of them are open pipe, some are closed pipe. And given the length of the pipe, you're asked to calculate the wavelength and then assign a name to the standing wave. So to assign a name, you can just look back on pages 446 and 447 in the textbook, and the sketches are there, and they are named as well. You'll be naming them using names out of your table of N values. It could be the fundamental frequency, it could be one of the overtones. And then, over on page 142, you're given a pipe, some are open, some are closed, and you're given the name of the standing wave, and you're asked to sketch it, to sketch what that wave would look like based on its name. Okay, so have a go at that, and we'll review it. And that is it. So here's a demonstration of an open pipe. So it's the same pipe with both ends now open. So this is a 288 Hertz tuning fork. We'll see if you can hear the standing wave.